All right, let's go ahead and continue with another topic that's very common in regression. And so our next topic is going to be that of residuals. And the residuals are part of a big, uh, almost for all regression models that you create, you will need to analyze the residuals. So let's start by just defining what the residual is. At its core, the residual is simply the error. So, in other words, you've seen that the line of best fit, the least squares regression line, allows you to predict for the corresponding response value, y hat, for really any x. And so remember, this is a prediction, the predicted response for any x value. So you basically input this. So I could go ahead and pick a value of x that was not given initially, and I can go ahead and predict roughly what the response value should be. Now, the error that's involved here would be for the actual data that we have. So in other words, for the actual data points, that's these guys right here. For these actual data points, we can go ahead and determine the error. In other words, the residual according to this model that we just created. So the line of best fit is essentially a way to summarize all of these data points. Obviously, it's not going to follow all of the data points exactly because that's not how we obtained the line. And so what that means is that even for values that we have in our data set, there's going to be some errors involved. So you can see that this data point seems to be right on the line. In other words, for that x value, whatever that may be, so let's call it x1, if you substitute that into your formula right here with the corresponding y-intercept and slope, then the predicted y value seems to be the actual y value. So there's no error. And part of that is because, remember, you go to the y variable, and that would be y hat. And it looks like that's the actual height of that data point. On the other hand, if you take a look at this data point here, so let's call this x2, then substitute that value into your formula, x2, and you'll get a corresponding y value. But remember that this basically says if you use this line. So if we use the line, you'll get a corresponding predicted y value that's right here versus the actual y value, which is the actual height of that data point. So you can see that there is a level of disagreement there. And that level of disagreement, which is basically the vertical distance of our point to the line, is what is known as the residual. So it's the vertical difference between these. So that's the residual. The residual equals the actual y value that I observed minus the predicted, which is really just written as y minus y hat. So you got to remember that every data point has an x and a y value. So it's fairly simple for us to go ahead and actually compute this because you have this x, let's call that maybe x3 comma y3. That's the actual data point. And then if you were to find the predicted point, so this point right here is x3 comma y3 predicted, you simply go ahead and subtract the actual value from the by the predicted value. And that right there is your residual. It's basically this vertical distance, right? Because that would be y actual, the height, minus y predicted. If you're above the regression line, then all of these residuals will be positive. I hope that that's clear because the y actual is greater than the predicted value because the predicted value is going to be on the line. So that'll be positive. Versus if you are below. So any value that's above, we go ahead and say that that's an overestimate of the prediction because you're predicting values on the line, but your data point's actually all on top. So here we have data points that are actually overestimating. Anyway, let's go ahead and do a quick example. So let's find the residual. Let's actually sketch it on the scatter plot for commute time. So remember, commute time is x of 35. if the commute, and then it says, is the commute time above average or below? And so what I want to point out is that this predicted line is actually the average response. Kind of like when we started talking about the mean, and we said that that summarizes all of my data. Well, the least squares regression line does the exact same thing, and so that'll be your average response. So first of all, let me go ahead and find 35. So this is 20, this is 30, and so 35 looks to be around here. And so this is saying if the X value is 35, what is the residual? And we do need to go back to our table up here. If your commute time is 35, so this is the actual value that's observed, notice that the actual Y value that's observed is 67.1. So that means that this data point right here has coordinates 35, comma, 67.1. So this is the actual X value, and this is the actual Y value that's observed. But if I go ahead and use my line of best fit, which we found above, so if the line of best fit was this equation, and we go ahead and substitute 35, that'll give me the predicted Y value. So let's go ahead and find the predicted Y value. I'm going to pause, and let's find the predicted Y value. All right, so using StatCrunch or just simply substituting, you can go ahead and find that the predicted Y value. So first we got to find Y hat. And we're using the fact that Y hat was equal to 69.0296 minus 0.0479. And I'm going to plug in the value of 35. Throw that into StatCrunch or using a calculator, we find the value is 67.35289, keeping 5 decimals. So now that we have the predicted value, that tells you the height that the line should be at. And you can more or less visualize this. So that's the height on the line. And so if you go horizontally, that value on the number line that we hit on the Y value is roughly 67.35. So this point right here is at 35, comma, 67.35. Let's round to 2 decimals just to keep things simpler. All right, and now we can find the residual. So remember, the residual is the distance between these. So that gap right there is the residual. And now I can use my formula. So now that I have the actual Y value and the predicted Y value, I can go ahead and subtract them. So my residual is equal to the Y value that's observed minus the Y value that's predicted. So our observed Y value was 67.1. Our predicted Y value is 67.35. So if we subtract, we keep 2 decimals, that'll be negative 0.25. So that right there is my residual. Notice that the residual is negative. It's negative. So let's write that down. So a negative residual implies that my actual observed data, in other words, my data point, this one right here, is below the regression line. And the fact that the regression line is the average, then that means that my data point that I observed is below average. which is the commute time. Data point is below average. Similarly, if your residual is positive, then that means that your observed data will be above the line, which implies that your data point is therefore above average. So it's higher than predicted. So here is a data point that is above the regression line. So that means that that data point, whatever the X and the Y value is, the actual observed Y value is higher than the predicted Y value. And that's fairly easy to see. So that data point is quote unquote above average. All right, that more or less does it for residuals. I want you to go ahead and try this in the next example. So this next example is has to do with the FICO score. So your Fair Isaacs Corporation credit score is used to determine your credit worthiness. It is used to help determine whether you qualify for a mortgage or credit, and is even used to determine insurance rates. FICO scores have a range of 300 to 850, with a higher score indicating a better credit history. The given data represent interest rate in percent a bank would offer on a 36-month auto loan for various FICO scores. So remember that these are the two variables. So we have variable credit score, variable interest rate, and every row is an individual. So for example, if an individual with a credit score of 545 goes into this bank, you can, it was observed that they obtain an interest rate of 18.982% versus a person that walked in with a credit score of 705 who was offered an interest rate of 6.68. So given this data, I want you to go ahead and deal with residuals. So let's just quickly review. Based on the problem that's given, I'm going to go ahead and say that the explanatory variable is credit score, because credit score helps determine interest rates. So it influences the interest rate. So the interest rate is the response. Now I can go ahead and find a linear equation that relates credit score to interest rates. So I simply would go to my data set, and I already have it here, credit score, interest rate, and we go to stats, regression, simple linear, select our X variable as credit score, and the Y variable as interest rate. And we can see that our equation is right here. So it's always the fourth line. You can also alternatively get your y-intercept and your slope from this table here. So let's write that down. So find a linear equation that relates. So this is y hat is equal to 61.36874 minus 0.07637 times x. All right, so let's go ahead and use this equation to predict the interest rate of a 690 credit score. So notice there was no credit score here that was 690. So that means credit score of 690. That means that X has to be 690 in that equation. So go ahead and give it a shot now and type in your answer. All right, so my predicted value here is, again, from 61.36874 minus 0.07637 times 690, and we get roughly 8.67. Now I can find the residual and sketch it on the scatter plot above for a credit score of 595. So what I want to point out is that whenever they ask you to find the residual, you got to have that value be observed in your sample. So 595 is observed in my sample. It's right here. So I'm looking at this individual. Here's the X value that was observed. Here's the Y value that was observed. So we actually need to predict this. Remember, the residual is Y observed minus Y predicted. And luckily for me, I already have the observed Y value. The observed Y value is 17.967. And then I need to subtract that from the predicted. So remember that to find this predicted value, you have to use StatCrunch, or you can simply go ahead and replace this value here with the 595. So go ahead and do that, and you should obtain the value of 15.929, I believe. All right, so once you have the X value, always go to your table and find the actual corresponding Y value, and then just find the predicted Y value. Do the subtraction, so just do the difference, and you end up with 2.03. All right, and that more or less does it. Now, I do want to go ahead and wrap up this video with a different topic, which is part of what D here gets at. So let's just quickly go ahead and predict the interest rate, that's the Y value, for a credit score of 800. And this is very simple. So we're going to say that the predicted Y value, when you plug in 800, is going to be 0.2734. Again, we get that number by simply replacing 800 in here, right? Because we're predicting. So we're evaluating that line when X is 800. So there's nothing stopping you from plugging in really any number. Now, what I want to point out, though, is that 800 basically says if you get that credit score, and notice there was no credit score of 800. It only goes up to 850. But this is that your interest rate should be 0.2734%. And that's kind of unheard of. Now, this gets worse if, for example, you predict with a credit score of 830, so getting closer to 850. According to this model, if your credit score is 830, then your interest rate should be negative 2.0173. And again, you get that by evaluating, actually replacing this X value with 830. And that doesn't make sense because interest rate should be positive. So what you're observing here is a problem. Our data no longer helps to explain what we're observing. Part of the reason is that our data that we observe here doesn't really allow, it only gives us information between 550 to set, so between 550 roughly to around 750 credit score. I don't actually know what's going on outside of that interval. So I don't know if the pattern continues or not. And so the reason for this is whenever you have data that is given over a certain range, you can think of this as the domain of the data or the scope of the data. So from the X value to this X value, that's the quote unquote scope of the data or scope of the model that we're going to create. It's very difficult for you to essentially extend outside of that. So as soon as you start extending, we're assuming that that pattern continues, but we don't have any data to back it up. So here you're essentially wandering into the unknown. We don't know if that pattern continues outside of the range of the data that was given. So that's called extrapolation. It's the act of extending an observed pattern beyond the range of the data, or outside the range. And extrapolation is really not recommended. Part of the reason is that you can essentially get lucky. You can go ahead and say, hey, if your data shows this pattern here, make it more obvious what we're pointing at. So if my data shows this pattern here, then maybe if you extrapolate, so in other words, here's your scope of the data or scope of the model, then if you wander out and you get a value like this, then that's amazing. You essentially have the same pattern outside of that data. But the issue is that most of the time, the sample that you got is really just a small fragment of a larger pattern. So for example, if we have this data here, only based on this data, we're going to create this model. So I'm going to create the regression line, which is given in blue. Make it in blue. That goes like this. So that's the regression line that I observed. And notice that that line does a pretty good job of summarizing all of the data that was observed. But unfortunately, it could be that the true actual function or the true pattern of the data is this red curve, like this. So that could be the true pattern that the data follows. Now, based on the data that I observed in orange, the blue line does a good job of explaining that pattern. But that's because we only had access to the data in here. This was the scope. If we have observed data outside, so notice if you have a new predictor that's outside and you're using the regression line, then you're going to get a prediction that's way out here. So this is the predicted Y value, when in reality, because we know that the true pattern is this red curve, the observed, the true value should be down here. And so there's no way for us to know whether we're going to get a good value like this or whether we're going to get a very poor approximation like in this one where we're predicting a value that's up there when in reality it should be down here. So in general, try not to move beyond the scope of the data, because there is no way for us to know whether we're dealing with something that continues the pattern like in the left or something that will deviate from that pattern that was observed earlier. So in general, try not to extrapolate. It's just not recommended. The estimates may be extremely inaccurate. And what we've been doing when it is accurate is when you predict with values like 690. So 690 would fit within the scope of the model, right? 690 is somewhere over here. We predicted at 595, that's here. We could even predict at, for example, like 610. And that's because the values that I'm predicting are within the scope of the model. And that's known as interpolation. That's the act of predicting within the known values. And so interpolation generally is fine because you have data in that range. Extrapolation is what you want to stay away from. All right, thank you guys for joining me. I'll see you in the next video.